okay? The first thing I'd like you to do, so we're going to take this model that we built last time, which basically involved comparing, on the one hand, a circulating infection in a system dynamics model, SIR here, to a comparable agent-based model where each person went through a set of states parallel to the system dynamics one, but where that infection within those persons was mediated by networks. Do you remember that? We had networks? Yeah, okay. So ladies and gentlemen, the first thing I want you to do here so that we can move quickly is I'd like you to go to main. So I asked you to open that one from the Moodle site. But if you'd like to follow along this with a previous one and just to double check, I'd like you to go to main and I'd like you to scroll down and observe the one thing I changed from last time, which is the connection range I changed. It was 30. I changed it to be 28.675, okay? And I'd like to run the model with this using the short duration of immunity one, where we had set the duration of immunity to be 10, okay? So here we go. We are going to run this at full tilt, the infection spreads, etc. And you may remember that what happened here was that we went, on the one hand, in the system dynamics model, into an equilibrium where we had the number of susceptibles and the number of recovered individuals both be equal proportions. The number of susceptible individuals was this green one here. Infectives and recovereds were both at this value here. And for the ABMs, we exhibited a prevalence which was alternating here in the general area of the number of infectives from the system dynamics, but it oscillated and was a bit lower. Why was it oscillating like this? Can anyone say? Why would this be oscillating? What's that? Why would it be oscillating around? Because of, yeah, stochastics. There's uncertainty. Where is there uncertainty in this model over time? Where is there some element of chance over time? Yeah, the connections between people, although those are static, but they mediate a sort of transmission over the connections, which picks a random person to connect to whom I'm already connected. So if I'm infective, I send a message to a random connected person around me. Where else is there stochastics? I don't know if you remember this thing. What was this branch put in to represent? Uncertainty about whether infection would stick, whether if I get exposed to infection, I stay infective. And in fact, there's stochastics associated with how soon I recover, how soon I lose immunity. And that contributed to this kind of wavy pattern we saw there. Okay, ladies and gentlemen, we are going to go on a fast pace to examine the impact of something that was important for governing the spread of infection and the transmission of infection, to wit, the connections betweenst people, these connections that knit people together. I had imposed last time by fiat a distance-based network where two given individuals are connected. Two individuals, A and B, are connected if and only if A and B lie within here 28.675 units of distance of each other. And I noted that each of these small squares, the tiny squares, was 10 units of that. Okay? And I noted that in any logic, there's a corresponding thing that translates that to meters, which we abstracted away from. Okay, so here we're going to have people connected to some number of others. I'd like to put in first machinery to allow us to see to how many people they are connected. Secondly, machinery that varies that a little bit to see another variant of that involving their connections. And then, moving on from that, I'd like to examine the impact of choosing different network schemes. Okay, we have miles to go and we have little time, so I'm going to ask you to follow me carefully. Okay, the first thing I'd like you to do is to go to open your palette, and I'd like you to go to the Analysis tab, and I'd like you to drag in a histogram, okay? A histogram. Histogram is shown here. What does a histogram show? Can anyone tell me? What's a histogram? Yeah, okay. So the x-axis will be sort of a value, often bins of value, so sort of ranges of values. This bin will represent things between 0 and 2. There's now the one between 2 and 4, the next one 4 and 6, say. And then the y-axis is a fraction or count of all the things, how many fell into each bin, okay? So you could think of it as kind of an approximation to a distribution. What fraction of the time does it fall in this bin, 0 to 2? Or what fraction of the time does it fall into the range 2 to 4, or the range 4 to 6? Does that make sense? A histogram allows you to summarize sort of a distribution in a discrete form. So it allows you to depict, okay, what fraction of the time is it in this range of values, or this range of values, this range. So if we picked 1,000 times, we might see a bell-shaped curve on a histogram. Does that make sense? Have you seen that before? Okay, so hearing no objections, I'm going to go on. This is a histogram. We're going to call this connection count histogram. Now, you'll notice before you use this, we're going to have to add in, use this in a useful way. We're going to have to add in what's called histogram data. So let's get that out of the way. We're going to drag in here next to the histogram something called histogram data. It's up here. It's called histogram data. We want to drag that in, okay? And this will be called connection count histogram data. But I'm going to actually do something a little bit more. I'm going to say index connection count, meaning it's going to be for a given person. We're going to create one later that's going to be for that person's friends. Okay? Okay. Index connection count histogram data. And then this histogram itself, we're going to go to, so we just dragged it in, and we are going to now, we could set the number of intervals and so on. We're going to go back to this histogram. We're going to say add histogram data, and we're going to say index connection count, meaning the connection count for the person of interest. Later, we're going to have it for their friends. So this is going to be a connection count, and we're going to refer to index connection count histogram data. That thing we just added in. That's going to be the data that we're getting. Okay? And then in the data update area, you can leave it as do not update data automatically. Are we okay with that? What did I do? Ladies and gentlemen, I went to the Analysis tab of the palette. Okay? From the Analysis palette, I took in, here we go, I took in a histogram. I then took in a histogram data. I called each of them respectively connection count histogram for the histogram and index connection count histogram data for the data item. And I made the histogram refer to that histogram data object. We're going to later add another one in here too, but this is going to be the first one we're associated with. And I made sure it's do not update. Are we ready? Any questions on what I've done? Hearing no questions, I'm going to proceed. I'm going to go to the agent palette, and I'm going to drag in an event. Okay? And this is going to be called populate histograms. In other words, we're going to histograms. We're going to do it. We're going to use this to perform actions. Ladies and gentlemen, AnyLogic observes what's called, like other inversion of control systems, it observes the Hollywood principle. Don't call us, we'll call you. We specify a lot of objects in here that, per the inversion of control principle, one of which representation is called dependency injection. Any logic takes care of calling the things we put in here. It's a framework, and we put in things, and it takes care of calling them, invoking them at the right times. Here we call in an event, and it's going to take care of calling it at time 0 months, occurs once here, and we're going to perform an action. This is the action which we're going to perform. Okay, now, ladies and gentlemen, the full horror of this class will begin, okay? So I'm going to expose you to one of my other great delights in life, which consists of functional programming, okay? So we're going to say this dot population, welcome to Java 8, this dot population, so I'm going to request the population dot for each. So for each person in the population called person, I'm going to take that person, I'm going to create a function that accepts that person, and I am going to add to this histogram data object that person's number of connections. So how do I do that? I will put this up on the big screen in just a second. So I'm going to do this dot index connection histogram data dot add. Don't worry, I'll go add it up there. Person dot get connections number. Okay, that returns the number of their connections. So I'm doing this for each. So let me go put this up on the big screen so you can see it in the full glory that it deserves. Okay, here we go. Get it here, and let's see if we can make this frob it so it's a little bit bigger. Oh, come on. Okay, mumble. I don't know if you can see that. Can you see that okay? So let me read it out to you. This dot population dot for each. So I'm saying for each person in the population, do this thing, this action. What is this thing here? What lies before us? What is the thing that I've highlighted in blue? That is a function. More technically, it's a closure. Okay? It takes in a person as an object, as an argument. In other words, it's a function that takes in a person, and with that that person, it gets their connections, the count of their connections, and it adds it to this histogram data object. Okay? Okay, so I go through each person in the population. For each person in the population, I tell them, do this, apply this function to them. That function takes the person. It says, I've got this person. I want to get the connections count of that person, and I want to add that in to the connections count histogram data object, which lies up here. So that for each person in the population, the count of their connections is placed in this object. And then where will that be displayed? In this histogram. Okay. Does anyone need to see this more closely? Does anyone want me to put it on a bigger screen? Okay, ladies and gentlemen, this is Java 8. It has closures, functions, and other things that delight the mind and heart. Okay, and then some things that don't. Okay, so ladies and gentlemen, I'd like to run this model. What do we expect to see? We have a distance-based network here. Two people, A and B, are connected if and only if they lie within 28.675 or something units of each other. What do we expect to see in terms of the histogram of the number of connections? Well, this is what we see, ladies and gentlemen. So what is this histogram telling us? Give me a factoid that this tells me. So I told you, I've explained again what histograms tell me. Tell me, what's something useful I know about from this histogram? Something, tell me something that strikes you from this histogram. Yeah, most people have about 10 friends. People have different numbers of friends. Some individuals here have very few, like 0 to 2. Some individuals have upwards of 20 to 22. Now, if we go and we click on this object up here, we'll see further statistics, such as the fact that the mean is, the gentleman in the back hit it bang on. The mean is 10, almost to the decimal point. That's not an accident. That was chosen by someone standing in front of you. And we also can get some breakdowns here. There's a standard deviation of 3.37, a sample standard deviation. The minimum is 1, the max is 20. So we have quite a range. For example, this person way out here has 1 connection, right? No one has 0, apparently, but some are densely packed. And ladies and gentlemen, that induces some dynamics associated with infection spread that we saw here. Great. So that summarizes for us the some features of that network. I'd like to do something a little bit more, ladies and gentlemen. I'd like to actually go and add in a new histogram data object here. Okay, here we go. We're going to add in a histogram data object, and this one's going to be called friends connection count histogram data. Note that I'm adding in not a histogram, but histogram data. A histogram is the chart. A histogram data provides the data for the chart. It bins it and so on. So I just dragged in from the palette, the analysis palette, I dragged in a histogram data object called friends connection histogram data. Okay? And I am going to go to the histogram, and I am going to add a histogram data object to refer to those friends. Instead of calling it index connection count, as I did above here, I'm going to call it friends connection count. Okay? And instead of being olive drab, I'll let it be deep sky blue. And this will be based on friends connection count histogram data. We could put this dot friends connection count to emphasize that if we wanted to. So now this histogram is going to include 2 histograms. 1 for each person in the population. 2 for the friends of people. Next, let's go to populate histogram. And here, ladies and gentlemen, we are going to do this in a more traditional way. We're going to do for person in the population. We're going to have an inner loop. Okay? For person friend in persons, okay, we're going to have to, and then we're going to have to handle a special case. So for maybe we'll do that up front. I'm sorry. We actually know everyone has a friend here, but let's just deal with it up front. If person dot get connections number is greater than 0, so if they have connections, then we will go through each of their get connections. Okay, each of this. So we're going to go through each person in the population. As long as they have friends, we'll get the connections of that person, and then for each of those friends, we will do what? We will add them in to the friend connection count thing. But you know, we can do this the same way, I believe. So I think we should be able to, let me just check this out. Person.getConnections, getConnections dot for each. Okay, we're cooking with gas. Here we go. What should go inside this for each? So for each of their friends, what should we do? Anyone want to say? We will add that friend to the friends histogram histogram. Okay, so for each friend, we will add in the count of those friends connections into the friends connection count histogram data object. Okay. Oops, not fiend, friend. Friends, I think it is. Okay, come on. Oh, come on. This dot friend, it's not a friends connection count histogram data. Okay, so ladies and gentlemen, we actually don't need this nice little curly there, so I'll just make it a little bit smaller. This is what I've added. So let me explain this again. For each person in the population, so I've just added this to the event. Beyond that code we had above, I said for each person in the population, we'll check if they have any friends. If they don't have any friends, we won't do anything. If they have friends, in other words, if their count of friends is more than 0, we will get their connections of this person, I should say. And for each of those friends, we will add the friends count of connections into the friends connection histogram. This code here that you see before you, this code is basically the same code as we had just above there for the person, except now we have friends here, and we're adding them in not to the index connection count histogram, but to the friends one. Do we see that? Who needs more time for that? Who needs that to be up there? Once again, we've used Java 8 enclosures here. Yeah, a little bit more time? Yeah, okay. So, ladies and gentlemen, each person in the population we're considering. Here's the first person in the population. We'll check how many friends they have. Do they have any friends? Nope. We'll go on to the second person. For that second person in the population, calling them person, do they have connections? Yes, they do. Okay. For each of that person's connections, we will call that person, call that connection friend in turn. For each of them, we'll call them friend, these connections of that person, and we'll add that friend's number of connections into the histogram data object. So I'm going to ask you to ponder this. What do you think the histograms will look like? All those people that are their friends are in the population. Do you think the histograms will look different or the same? Okay, same. Anyone think they might look different?
Ones that are highly connected will count for more.
Okay, because they will be represented. If that person's highly connected, they're connected with lots of other people, they'll be added into the friends histogram just once, or as many as they have connections. So it'll tend to over-represent people who are highly connected. Do you need more time? Anyone? Okay, let's run this thing. What do you think we'll see? So one group posits that it'll be the same, one group different. Ladies and gentlemen, the fox has shown its tail. Okay, so here we go. Which of them is larger? Well, we don't have to speculate. Let's go look at each of these. Here it even says the mean for each person in the population is 10. The mean for the friends is what? A little bit higher, 11, ladies and gentlemen. Okay, we see the friends have the same range, but they're skewed towards the higher end for reasons that Eric articulated. The friends tend to overrepresent people if you have many, many connections, lots of people are going to name you as a friend. You're going to be adding into that histogram many times. And therefore, it'll skew be large numbers of samples from things that have large numbers of connections because they're named as friends by many, many people. And hence, we have this paradox, seeming paradox, that if we consider people in the population and we ask how many connections do they have on average versus how many connections do their friends have on average, the friends on average always have more connections than the people in the population. So that's a point of note. But let's get on to a little bit more business, ladies and gentlemen. This was sort of a warm-up, and we'll be continuing on it next time. But I want to now that we know that there's 10 connections on average for each person in the population, and now we know what that histogram looks like, I'd like to change the types of networks shown. So I'd like you to go to main, ladies and gentlemen. We'll go down main. And I'd like you to change in main in the space and network area from a distance space network, ladies and gentlemen, to other types of networks. Now, to do this, I am going to change it from a layout type, the current layout type, to something called a ring-based network. It's going to actually just show them in a big ring for other types besides distance. So we're going to change it to be a layout type ring, and I'd like to change it to be a, ladies and gentlemen, a ring lattice network where the number of connections per agent is 10. Where did I get that 10? Whence did 10 come? Why 10? Yeah, it was the count of connections we had per agent. I chose that distance, 28.675 or whatever, to give us a certain number per agent on average of connections. And now I've just used that number of connections here as the number I want to have. So a ring lattice will arrange people in a ring. How do you think, if we place them on a ring, everyone's connected with 5 people to the left, 5 people to the right, how will that affect the spread of the transmission of infection? Will it speed it up? Will it slow it down? So everyone's holding hands in a large circle, except you have 5 hands on your left and 5 hands on your right. Somehow you're holding all of them. Imagine that. You're like an octopus or something. A decapus. How do you think this will affect the spread of infection? How will it affect the dynamics of infection, ladies and gentlemen? Do you think it'll speed it up? What's happening here? Do you see what happened? Did it spread faster or slower? It's actually spreading from behind this inartfully placed graph. So I'm going to move the graph. I'm going to move it up as I am wont to the area above this, so it doesn't occlude the real action. Ladies and gentlemen, does this speed up or slow down the spread of network? The spread of infection, rather, across the network. Does it speed it up or slow it down? You should be able to answer that simple question. Anyone? Oh, come on. Give me an answer. Did it speed it up? Anyone out there? I'm not purely speaking to the internet. Ladies and gentlemen, does it look like it sped it up? I mean, take a look at this graph now. Does this spread slower than before or faster? Slower. It took all this time to kind of creep up to this level. Before it went up pretty quickly and went over. Okay, next, ladies and gentlemen, I would like you to go to main, go down main, and we're going to switch it to a different sort. We're going to switch it from a ring lattice where we're connected to only people connected on either side of us locally, the closest people on either side of us. I'm going to change it to a random network. Now we're connected with people who are, any two people, A and B in the population, are connected with equal probability. The last one, we're connected only with people close to us. Same thing with the distance space. We're only connected with people close to us. This one, doesn't matter who two people A and B are, they'll be connected with a certain probability. Do you think that would lead to a fast or slow spread of infection across the network? Fast or slow? Yeah, fast spread. Why fast? Well, there's all these people connected with others. Well, think about it. I mean, think about the infection as a spark, right? It can spread not just the areas next to itself. It can waft in the wind and land on the other side of the network. Land in all these different areas. You can have these sort of express paths across the network, which lead it to spread very quickly. And you'll notice not only did it spread, do you notice something else about the blue curve when compared to the red curve? Now they are much what? Closer together. They actually follow very, very closely. The blue here follows the red almost precisely, and it oscillates in the vicinity of the red, crossing it. Not quite exactly the same, but crossing it. We'll talk about why not the same at another time, but it's extremely close. A random network, ladies and gentlemen, where people are connected with arbitrary other people is very similar to the sort of random mixing we see in a system dynamics model, where we assume that any person can connect to any other person. That, you know, for each person, if there's 50% of people in the whole population infected, for each person, each susceptible on average, they meet 50% of the people they meet are infectious, for example. We assume anyone can mix with anyone. Okay, let's go further than that. So there, it spread very quickly. Now let's go from a random to something called a small world. Ladies and gentlemen, a small world network is an interesting combination, also called a Watt-Strogatz network. It's an interesting combination, on the one hand, of a ring lattice network, where you're connected only with local people. And then, so at 95%, a very large fraction of your connections will be local, just to people nearby you. That's what you see in Maine here when we chose it to be a small world network. Here, 95% of my connections are with people nearby, my friends, my family, who tend to be close to you in proximity-wise. But then 5%, the other fraction of the connections, so 5%, those are the people who are much further away across the network, randomly connected across the network. So now we have a combination of those two cases, a combination of purely local, ring lattice, 95% of the time, with global on the other hand, reaching across the entire network. Just 5% of the connections, ladies and gentlemen, are across the network. But observe the dynamics. You get something that's kind of a mixture. It looks like it's got some elements of the random network, but it rises slower because it's still got a lot of locality. It hasn't risen quite as quickly with the random mixing we saw in the purely random network, but it does lead still to a closer approximation. Just those 5% of connections make all the difference. And finally, ladies and gentlemen, in the final thing we're going to do in this class, we're going to change this from a small world network, ladies and gentlemen, to a scale-free network, okay? Now, a scale-free network is going to be associated with a few hubs that have lots and lots of connections. Most people are going to have few connections, but a few hubs are going to have lots and lots of connections. And I'd like for you to, in the final comment here, to run it with a scale-free network. You'll notice there's too many connections to show effectively. We're we're not able to really see what those are. But you'll notice the characteristics here. Most people have a small number of connections, but some people have a large number. We actually need to, I made a mistake. We need to actually change that to be 5. The so-called M associated with this should be 5 here, associated with this in main. That's the parameter for the scale-free network. And approximately double it is the average number of connections. So if we change it to 5, it'll mean an average number of connections per person of about 10. And that will therefore preserve the basic features. So we have about 9.95 on average. But you'll notice the distributions. Compared to that original one where we had a distance-based network, what does this histogram look like? Is it wider or is it more compact? Is the region of support tighter or is it larger? Is there more variation in connections or less than the original one? Much more, ladies. The original is between 1 and 20. This is between about 0 and 120. So it simulates this situation where we have some people which have a very large number of connections. And look what it leads to. It leads to a very rapid spread and then a persistence of infection at some notable levels. But it leads to a very rapid spread within it. As initially maybe the infection starts in the periphery with a person with not many connections, but then it hits big time. It's like it hits the gasoline and it explodes, and it can spread to lots and lots of other individuals. So it actually rises very quickly. I'm going to ask you, before next time, I'll be posting a take-home exercise. It'll ask you to sort of look a little bit more closely at the histograms for each of these, and so we can talk about them next time. I'm also asking you to do a derivation of the fixed points of the system, and we'll see of the system dynamics model, and we'll see how the agent-based model compares in its prevalences. Okay? That's all for today, ladies and gentlemen. I'll be holding office hours for those who wish to talk about the assignment further, and I wish you good luck in finishing that. Thank you very much.